Thermodynamic geoengineering, negative cost carbon dioxide removal. Global warming is an excess of the same kind of energy as modern society requires to function. 93% of the heat of global warming has gone into the thermally stratifying oceans, making them receptive to the conversion of heat to work in accordance with the laws of thermodynamics and acts as a barrier to the efficient mixing of heat, carbon, nutrients, and the oxygen vital to life. Warming is a surface effect. If the heat could be well mixed throughout the ocean, it would require sophisticated and highly calibrated instruments to be able to detect it. Resplendi et al. In a paper, Quantification of Ocean Heat Uptake from Changes in Atmospheric O2 and CO2 Composition, estimated the oceans gained the equivalent of 409 terawatts of heat, about 20 times more than our annual primary energy consumption, annually between 1991 and 2016. Rao and Baird, in Negative Carbon Dioxide Emissions Ocean Thermal Energy Conversion, Neotech, demonstrated the stratification barrier can be broken by heat pipes that send surface heat into deep water where it is no longer an environmental threat and promotes mixing. The heat pipes that can overcome thermal stratification are passive heat transfer devices that employ phase transitions of a working fluid to transfer heat from a hot to cold reservoir. Melvin Pruitt, an experimental physicist from Los Alamos Labs, calculated 7.6% of the heat of warming heat can be converted to work, which is a total of 31 terawatts, or about 220% more energy than we are currently deriving from fossil fuels. The unconverted 388 terawatts is rapidly sent to a depth of 1,000 meters, from where it diffuses at a rate of 1 centimeter a day through the deepest water and 1 meter a day through the mixed layer to the surface, at which time it too can be recycled to produce more energy, in total 13 times, and the waste heat of the conversions is dissipated to space. The annual production cost of this energy ranges between $2 and $3 trillion, depending on whether the energy is used to produce an energy carrier like hydrogen or electricity that can produce value-added products and services at sea. This compares to the $5 to $6 trillion we are paying each year for fossil fuels, for half as much energy. Plus, the $7 trillion the IMF calculates is the environmental cost of doing business burning fossil fuels. 1 gigawatt of negative emissions ocean thermal energy conversion would provide 13 gigawatts of surface ocean cooling heat, while producing 130,000 tons of hydrogen, avoiding 1.1 million tons of carbon dioxide emissions a year, and consuming and storing, as dissolved mineral bicarbonate, approximately 5 million tons of carbon dioxide per year, resulting in an indirect planetary cooling of 2.6 gigawatts. For 31 terawatts, this cooling would sequester about 4.3 gigatons of carbon dioxide at no cost, whereas the electrochemical Neotech processes cost about $154 a ton. And since it would take 2,422 gigatons of removal to bring atmospheric levels down to the pre-industrial level of 280 parts per million, the cost this would be $370 trillion. Carbon dioxide levels have been increasing at a rate of about 2 parts per million a year, but 55% of these are absorbed by the oceans and land. So instead of 1,106 gigatons, we must remove 2,422 gigatons to break even. The service life of these plants is 30 years, so they would sequester 155 gigatons a year, or closer to 4,650 gigatons in total. With the result, the Earth's black body temperature of minus 23 degrees Celsius would soon follow. The point being, it is in our power to cool the surface while producing copious amounts of energy and mitigating every consequence of climate change without paying for carbon dioxide removal. Due to the high capital cost of thermodynamic geoengineering systems, it is necessary to prototype the system at a lab scale prior to scaling. The 300 watt per year prototype shown here serves 5 purposes. It reinforces the results of previous ocean thermal energy conversion experiments. It measures the carbon dioxide content of both an atmosphere and the water under the alternate conditions of a hot atmosphere and a cooler one, where theoretically cooling transfers carbon dioxide from the atmosphere back into the water. Different working fluids can be tested, and the power output of each can be compared. Different metals can be compared for their heat transfer properties, and the corrosion and heat transfer properties of the metals can be tested. Biofouling is a problem in all marine operations. But a recent expedition into the sunken battleship Arizona showed 75 years of corrosion of the metal inside the ship, but a pristine enamel tin drinking cup stood out starkly amongst the devastation. The oceans contain 47 different minerals and metals dissolved in solution. One of the most abundant of these is magnesium, at a concentration 3 times greater than of the carbon dioxide in the atmosphere. It is an excellent metal for the heat exchangers in a thermodynamic geoengineering operation but is corroded in salt water. Enameled magnesium heat exchangers would solve two of the greatest problems with thermodynamic geoengineering: corrosion and biofouling. Therefore, it would be worthwhile testing the heat transferring implications of enameled magnesium heat exchangers. A proposed lab-scale thermodynamic geoengineering prototype consists of 3 stacked acrylic aquariums, 3 meters in diameter and 2 meters deep. The bottom 2 meters is filled with cold ocean water. The middle tank contains warm ocean water and ambient air is sealed in the top 2 meters of the top tank. There are 0.75 grams of carbon dioxide in a cubic meter of the atmosphere. The volume of the atmosphere in the proposed lab-scale model would be 14 cubic meters, so it would contain 10.6 grams of carbon dioxide. Extrapolating from the Resplendy paper, about 28.6% of atmospheric carbon dioxide is derived from off-gassing from the ocean as it warms. This off-gassing can be reversed by cooling the atmosphere as was described in the Rao and Baird paper. A 1.8 degrees Celsius cooling from a baseline of 2050 down to pre-industrial should transfer about 3 grams of carbon dioxide from the atmosphere back into the water. The middle section of the prototype contains an evaporator where hot water enters at 30 degrees Celsius to boil a working fluid, resulting in a loss of 2 degrees to the water and a latent heat gain to the working fluid. A heater warms the water in the middle tank back to 30 degrees and a pump forces the warmed water back through the evaporator. The bottom 2 meters of the experiment represents ocean water at 4 degrees Celsius at a depth of 1,000 meters, which is pumped through a condenser that turns a spent working vapor back into fluid that is pumped back to the evaporator to complete the work cycle. And the condenser loses 2 degrees to the water, which is made up for by a cooler at the top of the system that pumps the cooled working fluid back into the bottom of the condenser. Carbon dioxide has been suggested as the working fluid for OTEC. It has the benefits of being less toxic, has a proximal density for the gaseous and liquid states at the relevant operating temperatures, and at full potential would utilize and remove from the atmosphere about a half gigaton of greenhouse gas. The thermodynamic properties of carbon dioxide and ammonia are similar, but the former operates at about 10 times the pressure, so the heat exchangers would need to be beefed up for a CO2 application. This image shows the size and obvious cost benefit of a carbon dioxide turbine in comparison to a conventional turbine. Thermodynamic geoengineering is an adaptation of the energy island concept invented by the architect and inventor Dominic Michaelis. It is a hybrid concept that combines OTEC, solar, wind, wave, and ocean current energies. Its principal drawbacks are the platforms are stationary, therefore subject to the vagaries of seasonal temperature differences, and the fact they use 81% of their real estate, producing only 19% of the total energy. Thermodynamic geoengineering reverses this ratio by minimizing the input of all ancillary energies beyond ocean thermal energy conversion and maintaining only sufficient ancillary energy to move the platforms through the water to force water through the heat exchangers. It is designed to seek out the highest sea surface temperatures in order to convert it to work. Dominic Michaelis was also the first to patent the deepwater condenser designed for OTEC used in thermodynamic geoengineering, which reduces the cost of the systems by a third by reducing the size of the piping connecting the surface to the deep water by 1 order of magnitude. The cost of these systems declines 22% with each doubling of their capacity, so the faster they scale, the more economical they become. This graphic shows a progression from lab-scale prototype to 1 gigawatt systems, be it as hydrogen or electricity generators, and the tonnage of carbon dioxide they are capable of sequestering. Zero-cost carbon dioxide removal, climate mitigation, and plentiful energy is available to a populace willing to put in the effort necessary to make it happen.